All right, everybody. So, couple of key corrections. You're going to want to listen to this. Listen up. On the conversions, most of you messed up on the temperature conversion at one place or another. Some of you, it was order of operations or just doing bad algebra. Remember how to do subtraction versus multiplication and do everything in the right order. The other thing, though, that even if you did all the math right and got 319.27, negative 319.27, if you didn't round properly, then you got marked down for sig figs. And this is one of the trickiest ones because the conversions involved both multiplication and addition subtraction. So we had to use both of our rules and we had to do them in the right order. You don't just round to 2 sig figs because you actually have to do subtraction first. Right? So if the temperature in Kelvin is 78 Kelvin and our conversion is Kelvin equals Celsius plus 273.15. The way we do that, we subtract that from both sides, right? So minus 273.15, and that gives us minus 195.15, if I'm remembering correctly. Yeah. That was just subtraction, right? Which means we're keeping the same uncertainty spot. We're plus or minus 1 degree here. This is plus or minus 1 degree. So it's negative 195 degrees Celsius. So now we've got 3 sig figs. And then when we plug it into the Fahrenheit temperature in Fahrenheit equals 1.8, which is exact, times negative 195 degrees Celsius plus 32. When we do this conversion, we're going to get another 3 sig figs, and then we're going to add the 32 to it. And so your final answer winds up being negative, is it, did I say 319? And you can round it to the ones place. So let me show the step there. 1.8 times negative 195 gives us what? Who's got a calculator out? That's the final answer before you add the 32 to it.
Wow. Negative 351.
Yeah.
So now before we can add the 32 to it, we have to round it to 3 sig figs again. And then that's an exact number again. So we'll keep it to the ones place. Pretty much always your temperature is going to, even though there's a multiplication conversion in there, it's pretty much always going to come down to keep the uncertainty in the same spot as your original number. Unless you have something really weird like if this was negative or was positive 519, then multiplying by 1.8, you can wind up with the sig fig taking into account. The way to make sure you always get it right on temperature is you've got to round with the right rule every step. If you do that, then you'll get it right. But you have to remember that you're switching operations. Yeah.
On the equation sheet that it gives us, like the temperature thing, it doesn't state that like 1.8 and 32 and 27 are exact numbers.
They're underlined though, right? Or asterisk.
There's an asterisk 1273.15, but there's nothing from 1.8 or 32. And I haven't asked.
So all conversions within the same system are exact. So I was including that. That is the only measured number out of that conversion. So again, it wasn't too harsh of a penalty because we're learning. You all will remember how to do that next time, right? So if you remember how to do it properly next time, then that's one half point well spent on that one. Any other outstanding questions that you want to go over, Maddie? Yes. Yes, I did. So the answer, the calculator answer for 2.3 was 667, or sorry, 665.5 moles. If we try to round that to 2 sig figs, that would be 670. But 670 is an ambiguous number, meaning it's unclear whether that's 2 sig figs or 3 sig figs once you round it. So the way that if you have an ambiguous number where it could either be 2 sig figs or 3 sig figs and you don't know which, you have to specify. And the way you specify is you put it in scientific notation. Diego?
That's still incorrect if you put it as.
I would have accepted that. I didn't see it. I don't think anybody did that, but I also graded these going pretty quickly.
Okay.
So I may have missed that. If you did write it like that, and still got marked down, come talk to me. But the way to do it, to make sure you get it right, anytime you have a number ending in 0, put it in scientific notation, and then it's always clear how many sig figs it is. And again, that was one that was really commonly missed. So any other clarifying questions? They can hang on to them. You can frame it, put it up in your room, make a scrapbook out of it. Also, if you're really good at math or are good at taking tests, you may be used to getting perfect tests in other classes. That doesn't really exist in the sciences. There's just too many small places. Even the best students I've ever had still got missed a sig fig somewhere. In fact, I don't think I could take my own test without getting marking myself down somewhere if I was under time pressure. So anything 50 points and up out of this section, that's pretty good on this one. And don't beat yourself up because you missed a half point here or there. Right. And remember, the rest of the class is structured so that even an F on this test won't sink you for the rest of the class. You could still get a B and average 50% on the tests in this class. Right. So keep turning stuff in, keep doing the work. Ideally we'll do better on the final, but it's not the end of the world. Vinny?
When's the staff gonna be ready?
On Wednesday. I'll have it ready for you. The next half will go fast because it's only 4 problems, right? So that's a lot easier for me to grade than all the small bits here. If I had another hour and a half this morning, I probably could have gotten it done, but such is life. Yes. I need to change up how I'm doing vocab because I did give a couple 10s, but for the most part, I need to be more specific about what I'm looking for. Orbital, I marked people down if you said it was a path or a ring, because it's really not as specific as that. It's more of an area, or most specifically like a volume or a function is kind of what I was looking for. If you said it was the path that an electron takes, electrons don't move in a straight line. So it's not really the path an electron takes. And for nucleus, I was looking for full credit on nucleus. I was looking for something involving either protons or neutrons or positive charge. If you just said the middle of an atom, you got half a point off. Again, not a huge thing, but I was looking for something a little bit more specific. And if you put the center of an atom and you got marked down a half a point, I'm not going to go back and regrade them all right now, but if that half point winds up being the difference between you getting an A and a B at the end of the class, remind me about that. And it won't be what makes or breaks your grade. Right. And that goes for any half point correction. If there's something, especially if you can make the argument that it shouldn't have been a half point off, I'm more than willing to go back and give you those points. But for the most part, it's not going to matter. Half point's not going to make or break you. Maddie? So I got a lot of the weight of a molecule. If you wrote the weight of a molecule and didn't give me any units, then you got a half point off. So I was either looking for something like sum of the atomic masses or in AMU or grams per mole, or add up all of the nucleons, all the protons plus neutrons, something a little bit more specific than just the weight of the molecule. The other one that I will say was a fairly common mistake is on the 3p6 question. If you just explained it in terms of the periodic table and not what it actually means, then you got a half point or a point off depending on how well you explained it. But if you just said third row P block 6 columns in, that is kind of how we find our electron configurations. But the electron configuration, the 6 actually means how many electrons are in that p orbital, not just that you're in the 6th column. So if you've just talked about it in terms of columns and rows, then you got a small deduction, even though that is part of the right process. But that's not what the term actually means. All right. And again, if you feel like making the argument, I don't want to open it up to debating grades too much. But if you think you really did a good job explaining it and still got marked down a point, talk to me after class. I probably won't change your grade. But you're welcome to make the argument. Because I have changed grades in the past. But there's chemists love to argue. Chemists are the lawyers of scientists. Because the physicists aren't right and the biologists aren't right. It's the chemists that are right. All right. Then let me get some slides pulled up. We're going to talk about energy. So next couple topics we're going to talk about energy. And then we're going to talk about stoichiometry and energy and how all that works together. And then we're going to start talking about phase change and intermolecular forces, because all of those topics kind of tie together. But it's going to feel a little disjointed at first until we get to phase diagrams. So let me pull up slides. I think there was a 57.
I know the last score. Yes.
This is the one that cost me 6 points.
What matters is nobody got it perfect. Your family from Minnesota? What about you? Okay, my wife grew up in New York. Yeah, nice. All right, everybody. Let's talk about energy. Energy is kind of a cool topic because it's fun to learn about, because it's one of those things that shows up everywhere in pop culture and everyday life. But for the most part, nobody's been taught yet how do we actually measure anything like this, or how do we calculate any of this. So there's they're not particularly long, but there are definitions and derivations that you'll learn when you take physics. But basically the definition of energy is usually, it means that you can change the velocity of something else. If you have energy, it means that you can change the velocity of something else. You can accelerate another object. And the act of accelerating another object is called doing work. Work is the act of changing something else's velocity. All right, so anytime you have motion in mass, you have some amount of energy. Right, so the classic definition in physics is kinetic energy, which in kinetic energy means energy in the form of motion. So anything that's moving has kinetic energy. Because if something is moving and it has mass, what happens when it bumps into something else? It'll transfer some of that energy, right? Think about pool balls on a pool table, right? If one of those balls is moving relative to another and it bumps into it, it transfers some of that kinetic energy to the stationary ball. Right? So the original definition from physics is kinetic energy is equal to 1/2 mass of the object times the velocity of the object squared. And you have to have mass, because if you don't have mass, it doesn't matter if there's velocity. You can't change anything's direction, right? Which everything has mass. So we can't really do this experiment. But if you think about trying to play pool with a ping pong ball as the cue ball, it's not going to work very well, right? Because no matter how fast that ping pong ball is moving, its mass is so small, it's not going to be able to give away much kinetic energy to anything else. Now, there are other things at play there, like inertia comes into play. And we're not going to talk about that too much. But this is our original definition. And if we put everything in physics units, what do you measure mass in physics? Anybody had up, or just measuring mass of an object? In chemistry, we'd use grams. Newtons is a force, not a mass. You're headed the right way, though. But in physics, we're dealing with larger objects, so they don't actually do grams, they do it in kilograms. And if we're measuring something's velocity or speed in a physics class, we're talking about a baseball or a pool ball or something, what units do we use for velocity? Meters per second. So energy has these weird units that look like kilograms times meters squared per second squared. That doesn't make, those units don't make a whole lot of sense on their own, but they come from the fact that you have this combined variable that we call energy. And so basically, anytime you get something like this in physics, what physicists like to do is they just redefine this as a new unit. Say, okay, well, kilograms times meters squared over seconds squared doesn't make any sense. So we're just going to take this whole thing and call it a joule. So a joule is a unit of energy that's made up of these other units. And I heard somebody say newtons earlier, Brady. Yeah. And that's a force unit. The definition of a force in physics is a mass times the acceleration. So when you have kinetic energy, you exert force, and that's the mass, and then how much you changed its speed. So units for force, and this is less important, but just since you brought up units, it's still going to be kilograms, except acceleration is meters over seconds squared. Meters per second is how you measure change in velocity. This unit is called a Newton. So, and again, we're not going to do much with Newtons in this class. We'll talk about them a couple other times, especially when we get into talking about pressure and gases, because it turns out Newtons are a good way of explaining how gases can exert force and do work on other things. Can anybody think of an example in everyday life where a gas exerts a force on something else? In a car. What specifically do you mean, Vinny? Combustion? What does combustion do? Yeah, by when you burn something in a car in an internal combustion engine, that combustion produces gas molecules and also heat. And when you give those gas molecules lots of kinetic energy, they can exert a force by expanding a piston and making that piston larger. That not really the piston doesn't get larger, but the volume of gas gets larger. It pushes the rod from that piston, and that causes wheels to turn. It causes that motion. So that's an example of where we're going to use it in the future. When we talk about gases, we'll actually measure the force of a gas in terms of newtons per square meter, which has its own name that we won't get into now. Basically, like I said, anytime we get these really weird combined units, a lot of times we'll just, especially in physics, we just rename them. Chemists notoriously make up units before they actually have a place where they came from. Physicists are better about waiting until they actually have a derivation before they name units. Does anybody know another unit for energy besides joules? Watts is technically power, which is slightly different. Say it again. Hertz. Hertz is frequency, which is proportional to energy if we're talking about light. Calories, that's what I was looking for. Anybody know the definition of a calorie?
Oh, no, I remember.
It's the energy required to heat up 1 gram of water by 1 degree Celsius.
Yeah.
So that's easier to measure in terms of chemistry, but it doesn't actually explain what energy is the way that this does. So the two common units, a calorie is defined as energy required to raise 1 gram of water 1 degree Celsius. That's kind of a weird unit though too, right? But if you think about energy as being something that changes temperature, then it kind of makes sense. If you're warming something up, then you're giving it energy. How does that work? If energy is defined as the ability to change something's velocity, we can calculate it in terms of mass times velocity of an object. How does that tie to heating up water? What are we? And energy, or kinetic energy at the molecular level, we think of as temperature. I'm going to avoid using the term heat because we use the term heat too much. In everyday life, you might say something has a lot of heat when it's hot, right? We're not going to use that terminology, that way of phrasing it here, because we're going to use heat in 2 other ways, at least 2 other ways. And it'll get way too confusing if we say that. So what we can say is that at the molecular level, if we get all the way down to the atomic scale, kinetic energy at the atomic scale is proportional to temperature. Basically, the hotter something is, the more kinetic energy the molecules have. And there's a lot of, we can use that to actually work backwards and explain why when you touch something, it hurts. Or why burns are caused when you touch something hot. Basically, what happens is if you transfer too much kinetic energy to the molecules in your proteins and in your cells, those proteins basically fall apart. The atoms start moving too fast, and the whole thing loses its structure. You can think of a protein as a really big, elaborate Lego sculpture. If you took a Lego sculpture and you started shaking it like this really fast, what's going to happen? It's going to fall apart, right? Or at least parts of it will. And when that happens, that's actually what causes a burn, is actually the denaturing of proteins in your skin. And then your immune system no longer recognizes some of those proteins as being native to your body and basically tries to get rid of them, which is what causes the blistering. If you actually get to like 3rd degree burns and like blackened skin, charring, then that's actually oxidation happening and you're actually breaking apart those molecules even further. And so that's a different response physiologically. And I don't know enough about physiology to be able to explain what happens when your body tries to heal a 3rd-degree burn, so I won't try. Potential energy is the other type of energy, and potential energy is basically energy that's not kinetic energy. It's sort of a really broad definition. Anything that is energy but isn't movement is potential energy. So for instance, this bird has some amount of energy, right? If the higher I move it though, the more potential energy it has, because if I dropped it, it would be moving faster and have a higher velocity by the time it hit the table. If I drop it from here, it has barely any kinetic energy by the time it hits the table, right? So the height of an object is related to how much potential energy it has. That's the classical way of thinking about potential energy, is basically how far can something fall. In chemistry, Asa?
Much energy to rise it to that point as it does generate by falling.
It does. You have to, conservation of energy says you have to put as much energy into it as it now has in potential energy. So I had to exert a certain number of calories or joules to raise the bird up this high. And then when it falls back down, it would give that same amount of energy back. So other than the fact that E equals mc squared gets weird and nuclear reactions are weird, for the most part, conservation of energy is a pretty good way of thinking about things. If you have a change in energy, that energy has to come from somewhere or it has to go somewhere. So in terms of chemistry, we usually think about potential energy in terms of chemical bonds or how unstable a molecule is. If a molecule is really unstable, that would be like me taking a bird and balancing it right here. That's pretty unstable, right? If earthquake happened, that bird has a long way to fall and it's a little precarious up there, right? So if we make a chemical structure that's unstable, then it has a tendency to react. And when it reacts, it releases some of that stored potential energy in terms of kinetic energy. It converts some of that potential energy into temperature change. Right? So what's an example of a reaction that that causes a temperature change? We already used cars. What else causes a temperature change when a chemical reaction happens?
I felt like you do the elephant like toothpaste experiment thing.
Elephant toothpaste. What happens when you do elephant toothpaste?
It bubbles up and it creates a lot of heat.
It bubbles up, and the bubbling up is actually mostly just from dish soap. It generates a whole bunch of oxygen really and very quickly. But it doesn't, that'll all just be lost. Like it would look like boiling water, basically, just bubbling gas, unless you have some dish soap mixed in with it, and that's what makes it look like toothpaste. But it also generates a lot of heat when you do that, because you're starting from some molecules that are unstable, in that case, hydrogen peroxide, and you're basically letting the hydrogen peroxide react to become more stable. And in that process, that's like our bird falling from up here, falling down and becoming more stable. But in the process, it gains a lot of kinetic energy. Any other examples? Dehydration, anything in particular? So dehydration, a lot of biological reactions are going downhill in energy. They're becoming more stable. And so height and sort of elevation, or how high something is a really good way to think about how stable molecules are as well. So we'll see a lot of examples where I'll draw what's called a potential energy surface, where I'll draw for a reaction. I might draw something that looks like this. And what this is saying is if we start with our reactants with this much energy, and then give them a little bit of boost, they're actually going to go downhill in energy and finish down here. They're more stable because they're lower in energy. And the difference between these is going to wind up being given off to the surroundings. So we're going to talk a lot about energy as height, basically, even when we're talking chemically. It's not strictly speaking height when we're talking about chemicals. I did draw this one going from top to bottom, but that was just because that's where the space was. But octane, that molecule at the top, and oxygen are inherently unstable molecules when they're mixed together. And if you let them react, they make CO2 and water. And in doing so, CO2 and water are lower in energy than octane and oxygen were to begin with. So in that case, the difference in energy between where you start and where you end can actually be calculated. But before we do that, we're going to need to know how we're going to do this in terms of chemistry. Since we're not going to be measuring the velocity of molecules directly, we're for the most part going to be measuring velocity of molecules in the form of temperature. All right, so a couple other notes about units. We're going to, for the most part, we're going to stick to calories and joules. Joules is really the better option, but there's still a lot of textbooks still use calories. I was taught calories and used calories in grad school more than any other energy unit. So I tend to slip into talking about them in terms of calories. But joule is actually the more standardized SI unit. We did talk about calories in here back at the beginning of the class, didn't we? At least a little bit, maybe one of those random questions. The amount of energy required to raise 1 gram of water 1 degree Celsius is actually a really small number. And 1 joule is actually a really small amount of energy as well. So even more commonly, we talk about kilocalories or kilojoules. So 1 kilojoule is equal to 1,000 joules, and 1 kcal is equal to 1,000 calories. And how does that show up on nutritional facts on with a capital C? Yeah, it says calories, but if they're doing it right, then it'll be with a capital C so that they can avoid writing kcals, which again, pet peeve of mine. It's a new level of phobia of metric units, which actually that is a phobia that actually has a name. You can look up phobia of metric prefixes. And that's a real thing, apparently. I always say that as a joke, but somebody actually called me on that and looked it up, and it's a thing. And the more we get outside of chemistry, the more we'll see other energy units. Mechanical engineering, they rate energy in terms of BTUs, which stands for British Thermal Unit. Is kind of an old school unit, but gets used a lot in terms of furnaces. Anything that's going to put out heat, they rate that heat output in terms of BTUs. So if you ever have to buy a furnace, you'll probably look at their specs in terms of how many BTUs does it put out. And actually, I think that actually shows up in computer engineering too, when they're talking about designing cooling systems for the inside of computers, because processors and GPUs put out a lot of heat. And so they actually have to be cooled, and they rate how much they can be cooled in terms of BTUs sometimes. Physics and electrical engineering use EV, which stands for electron volt, which is, I understand why the unit exists, but it's not very practical. It's not a useful energy. It's basically, it's similar to AMU. We don't really use AMU, atomic mass units, to talk about atoms, right? Because AMU would be like carbon is 12.011 AMU. That's the weight of a single carbon atom. That doesn't really make any sense, right? Because we never do things one atom at a time. EV is the energy equivalent of that. It's like if you let 1 electron move 1 voltage, to become 1 volt more stable. That's an electron volt. So again, it's like, okay, I understand why it exists, but nobody ever really uses it. If you're buying natural gas in bulk, if you're a utilities company and you're buying your natural gas and shipping it through pipelines, then you might buy gas in terms of therms, which is 100 cubic feet of natural gas at a specific pressure. Which is also kind of related to barrels of oil equivalent, BOE, is literally if you took a 55-gallon drum of oil and burned it all, that's the amount of energy in 1 barrel of oil equivalent. So some of these are weird. Kilowatt hours is an energy unit because power is energy per minute or per time. So like if you expend energy per second, like one of these lights puts out or requires so many joules per minute. Joules per minute is power. If you take that and you multiply it by a time unit, you get energy back again. So kilowatt hours, since watt is power, a power times a time is an energy unit as well. And lastly, just because it's kind of fun to think about, well, fun might be the wrong word, but tons of TNT is actually an energy unit. And that's how they rate explosions. A metric ton of TNT is 1,000 kilograms of TNT. Asen? It's not a great unit, except for the fact if you're trying to design bombs during wartime, it's effective because it's basically mostly used for explosives, for rating explosives, because different explosives have different energy capacities. So for instance, the bomb that was dropped on Hiroshima was, if I'm remembering this right, was it 15 kilotons? So 15,000 tons. So 15 million pounds, 15 million kilograms of TNT detonating all at once. It was similar to the amount of bombs that were dropped on the UK over the course of all of World War II was detonated in one explosion. So when you're trying to compare different energies from really big sources like that, it gets used, but yeah, nobody has an intuitive idea of what 1 ton of TNT detonating looks like, other than just it's really big. Anya?
Energy the atomic bomb had?
So that was the bomb over Hiroshima I think was 15 kilotons. The largest one ever detonated. There was the Soviet, Tsar Bomba. There was a 50 megaton bomb that was detonated by the Soviet Union as a test, and they designed one that was 100 megatons. So 100 million tons of TNT detonating all at once. And there's some websites that'll actually show you, like, you can say, okay, if Tsar Bomba was detonated in Reno, if the 50 megaton version of the Tsar Bomba was detonated over Reno, everybody in South Lake Tahoe would still have 2nd to 3rd degree burns all over your body. And it would break windows as far away as Placerville. So obviously it's an oversimplification because it just treats everything like it's a sphere, and really we live at the bottom of the bowl, so we might be protected by the mountains slightly. So there's other factors that go into it. But obviously you don't want to be too close to a nuclear bomb when it goes off. And this is not including things like radiation sickness and fallout and all that good stuff that comes along with after the explosion. I never did make it through New Vegas. Fallout 3 was good though. This is just kind of a fun graph. It's a log scale. This is also a fun time to talk about log scales, because a log scale means every one of these lines is 1,000 times greater than the line before it. So if you sleep for 1 hour, that's about 10,000 joules of energy. Or 10 kilojoules, right? So it's 10 kilojoules to sleep for an hour. If you exercise for an hour, it's only 10 times more than that. So it's 100 kilojoules. No, sorry, 1,000 kilojoules, which is about 250 calories, nutritional calories. You keep going up this, so energy from 1 gallon of gasoline is about 100 times greater than the energy in 1 serving of pasta. So if we had the capability of actually like processing gasoline as energy source, we could, in theory, 1 gallon of gasoline would be equivalent of 100 servings of pasta. It's actually fairly energy dense. It's kind of one of the reasons why it's hard to get rid of fossil fuels. Is it turns out fossil fuels are actually just incredibly convenient and they are fairly energy dense. If you made a combustion stomach, that's effectively what we're talking about, right? You would only need a little bit of fossil fuels. And to put that into context, if you did the same thing with uranium, if your body could process the energy in uranium, it would take 1 teaspoon of uranium to give you enough calories for your entire life. This nutritional calories, not in terms of the energy that we use in terms of using lights or computers or anything like that. Maddie?
I'm sorry, this is kind of off topic. Going back to-
We're already off topic. Go for it. Yeah. Probably not Lake Tahoe, but it would definitely change the drainage pattern depending on exactly where it detonated and how high up. It might break down the basin enough that Lake Tahoe would no longer exist, because you can imagine like breaking a hole in the wall of a bowl, water could flow out then, right? But
If they dumped it in water, would I be safe with the first?
initially you wouldn't be safe from the radiation. It depends on how close you are, really. And if shockwave is also a different thing. It's more than just the heat and the light that comes from the bomb. There's also the shockwave that comes from the bomb and all the radiation after the fact. Well, a fallout shelter, basically being inside of like 10-foot thick concrete walls underground so that nothing's going to collapse on top of you. Even that only works as long as you're far enough away from the initial blast. Yes.
Yeah.
You would, yeah, because airplanes only fly a couple miles above the surface of the planet. And so if you were flying on an airplane and you happen to be near that, it's just as big of an issue. It's a sphere, right? It's not just on the ground. I'll see if I can find that link. There's a nuke map. Yeah. Yeah. And you can play around with things. Try detonating different bombs in different places and see what it looks like on the map. All right, one more point before we start doing calculations. So energy use per person in 1 year in the US is 10 to the 11. 10 to the 11 joules is average energy use per person in 1 year in the US. This is from more than 10 years ago at this point, so that's not all that accurate. It's probably about the same. We use electronics more than we used to, but at the same time, lights and LEDs and things in cars have gotten more efficient in that amount of time. So it's still probably a decent estimate. Solar energy reaching the Earth per second is 10 to the 17. So there's enough energy reaches the Earth per second that you could actually, that's enough for 1 million people for a year. If you could turn it all into electrical energy or into a usable form of energy. Most of that is light energy that just gets turned into heat. So we can't actually use all of that. But basically, this is one of the reasons why everybody thinks solar is gonna be the biggest solution to getting off of fossil fuels, and it will be a big part of it. Because there's so much solar energy that gets to the earth every second. In fact, if only 1,000 seconds of solar radiation is enough for the entire US for a year. In 1,000 seconds. That's not all that much, right? That's under an hour, 3,600 seconds in an hour. So it's like 20 minutes. 20 minutes of solar energy. If we could capture all of it and turn it into usable energy.
Daylight savings time.
And then last but not least, look at energy radiated by the sun per second. That's another 10 to the 9 times more than what hits the earth. So 10 to the 9 is a billion. So only 1/1000th of the sun's energy actually hits the earth. Where does the rest of it go? Into space. This is why every planet gets cooked. Also why one of the ways that turns out xenobiology and search for extraterrestrial intelligence is a legitimate scientific field you can go into. There's, well, at least there used to be funding from National Science Foundation to actually give money to people looking for extraterrestrial intelligence. And one of the things that's been postulated that any fairly advanced society would actually find a way to use that other energy. So you can imagine putting a sun in the middle of a solar system. We're just getting one tiny bit of that sun's energy. How could we capture all that sun's energy? Not. Yeah. It's actually, there's a scientist named Freeman Dyson, which just incidentally is just a cool name. Yeah, who came up with the idea of a Dyson sphere. He didn't name it after himself. Which is basically the idea that you just enclose your sun in solar cells. Or basically make it the inside of a big ball. Would be lots and lots of space then. We wouldn't run out of places to live. We could capture all of that energy.
No more light.
We don't know. So we're not that level of a civilization yet. A bunch of mirrors. It's actually where the idea for the video game Halo came from. It's basically it would take more mass than we actually have in the entire solar system to make a sphere like this. But if you made a ring instead of a sphere, you could make it like 2 miles wide and go around the entire orbit of the Earth. It would take about the mass of Jupiter to make a structure like that. And Halo got that idea from an author named Larry Niven, who was also a scientist. Actually, I think it was 100 miles across, 100 miles wide around the entire sun. All right. One thing that's actually going to be useful. This has been fun. But let's talk about how we're actually going to calculate some of these numbers. We're not building Dyson spheres or Tsar Bombas or even ring worlds yet. If we want to calculate how much energy changes hands, we're not going to be doing that by measuring the speed of molecules individually, right? If we want to know how much energy is changing hands in a chemical reaction, we look at change in temperature. Because a change in temperature is going to be proportional to the amount of energy that went into a system or came out of a system. And if you think about putting a pot of hot water on a stove, you have to put energy into that water to bring it to a boil. the way we calculate that is we look at what the material is and how much of it we have. If I filled up a 5-gallon turkey fryer full of water and put it on the stove, is that going to boil faster or slower than just a regular saucepan? Slower. Why? There's more water, right? More water means we have to dump more energy in because we have to bring all of those 1 grams of water up to a higher temperature, to the same temperature, right? So the mass of the object that's changing temperature is also going to come into play, right? And so the heat equation that we use in chemistry is Q is equal to M CP delta T, which looks intimidating. Don't worry, we know what all these terms are. We have to define them. And that's the easy one. What is M? Mass, usually in grams. What is delta T? Temperatures, capital T. Right, so be careful, not lowercase t, because then it would be change in time. We don't want to get into that because that involves differential equations and multivariable calculus. So we don't want to look at the rate of heat transfer. We only want to look at total amount of heat transfer. You'll get there eventually if you take more science. So change in temp, usually in degrees Celsius. Q, here's where we're actually going to use the word heat. Heat in sciences means thermal energy transferred, not just how hot something is. How hot something is, that's just temperature. Heat specifically is talking about transferring energy from one thing to another. So the amount of energy that goes into a system is going to be related to the mass of that system, the temperature change of that system. Usually this is going to be in joules. This other term, this is why it gets really confusing to use the word heat, is specific heat. So we've got specific heat being used to calculate the total heat. Specific heat is kind of like our definition of a calorie. Specific heat is how much energy does it take to change 1 gram of a substance by 1 degree Celsius. Right? Because not everything takes the same amount of energy. If you put an empty saucepan on the stove and turned it on, is it going to heat up faster or slower than if it's filled with water? If it's empty, faster. It turns out water actually has a very high specific heat. Water takes, which is another way of saying water takes a lot of energy to get it to change temperature. It's sluggish, right? Metals have a really high, or they change temperature much faster because they have a very low specific heat. So our unit on specific heat is going to usually be an energy unit per over grams degrees Celsius, which looks like a weird unit, but it actually makes sense when you think about the definition of a calorie. That definition of a calorie was the amount of energy it takes to raise 1 gram of water 1 degree Celsius. So in other words, joules per gram per degree Celsius. Right, and just to give you an idea of the difference, so that the specific heat of water is 4.184 joules per gram degree Celsius. The specific heat of copper is about 1/10 of that, is about 0.4. Hannah? Or I'll give you specific heats if you need them. And specific heat of water is what we use most often. This one is one of those ones you're going to wind up memorizing just because we use it so much. But if you need a different specific heat, I'll give it to you. Because who memorizes things when we have the internet, right? All right, so how does this equation work? So like I said, it looks kind of intimidating. It's really obnoxious that Q doesn't have any of the letter, it's not any of the letters in heat, but this is what we're working with. The heat transfer into an object is equal to the mass of that object times the specific heat of that material. So copper has its own specific heat, water has its own specific heat, plastic has its own specific heat. Every type of plastic has its own specific heat. Right? So you need to be given some information or be able to look it up to get this. Delta T, well, it's a Greek letter, but it's really just change, right? It's not that big, that hard to work with. So here's an example. If you burn 1 gram of table sugar, it produces 16.5 kilojoules of energy. If all of that energy goes into 120 gram sample of water, what's the temperature change of the water? Yes.
Right.
There will be change. You can even be more specific and say it's going to go up. Temperature change will be positive. Are we given enough information here?
Yes. Yeah.
What are we solving for?
Change in water temperature.
So we're solving for delta T, so we need the rest of the variables to be accounted for, right? What's Q going to be?
16.5 kilojoules.
16.5 kilojoules. What's mass?
100.
And how do you know that?
Oh, no, that's actually.
Because that 120 grams, there's 2 masses in this problem, right? But the water is what's being warmed up. So we're going to use we want to be specific, we're using the mass of the water. What's CP? It's on the slide.
Oh, yeah.
4.184. This is the other way of writing. If you see anything raised to the -1 power, that's the same as writing over that unit. Right? So sometimes if you're trying to type things and keep it all in the same line, you'll see it written that way. Gram to the -1, Celsius to the -1. But that's just another way of writing joules per gram per degree Celsius. So is it that easy? Watch out for units. Remember I told you that a joule is a pretty small amount of energy? Our Q is measured in kilojoules, but CP is in joules. So we just got to change kilojoules to joules. 16,000, 1.65, 10 to the 4 joules. But then, yeah, it really is that easy. Plug everything in, solve for delta T. Even though it's 2 letters, we're going to solve for that as 1 variable. Right, so delta T equals 1.65, 10 to the 4 joules over 120 grams over 4.184 joules per gram degree Celsius. Now, considering most of our units are just going to cancel out, it's tempting to not bother writing this big obnoxious unit at the end. I would encourage you to always write these units. Even when you know what they're supposed to be or what your final answer is supposed to be, because it'll remind you if you messed up by forgetting to count kilojoules into joules. Or if you're given calories instead of joules, you have to convert calories to joules before you can use this, right? So writing out your units is a good way to remind ourselves how that's all going to work. We'll get joules cancels joules, grams cancels grams. Our final units will be 1 over Celsius, which is the same as what? Celsius. 1 over Celsius is Celsius. You guys remember how dividing fractions work? When you divide fractions, is the same as multiplying by the reciprocal, right? So if you have 1 over Celsius, that's like saying 1 divided by 1 over degrees Celsius.
Attention staff and students, softball players, girls, please take bus F to practice. Again, softball girls take bus F to practice.
So if we actually are showing our work for this, we're going to multiply by the reciprocal, which looks like degrees Celsius. All right, so our final answer will be in Celsius, which is what we want. What do we get for a number? 16,000 over 120. 4,000. What is it?
Well, one sec. I got 32.863, which is gonna be 32.9.
Good. Is that a reasonable number? 16,000 divided by 4 is going to be 4,000 divided by 120. Yeah, something around 40 seemed reasonable if we round. So 32, I'll call pretty close to that. Which is a little bit wild to think about because 1 gram of sugar is not that much, right? It's enough to take 120 grams of water and raise the temperature 33 Celsius, which is 60 Fahrenheit roughly. But it turns out there's a lot of energy in sugar. All right, so if the temperature started at room temperature, if the water started at room temperature, what's the final temperature going to be? What do we have to do to figure that out? What's room temperature? 70. So if you're thinking in Fahrenheit still, you just made more work for yourself because you got to convert 70 Fahrenheit into Celsius before you can add these. Or you could know that 21 degrees Celsius is about 68 Fahrenheit. Actually, that one's exact, I think. 21 Celsius is 68 Fahrenheit. So if we say that our initial temperature is 21 degrees Celsius, and we're going to add 33 to that. So we'll get something around 50 Celsius. And if you want it, the other key with this delta term, it's change in temperature, right? Which mathematically, how do we write delta? Well, sorry, like this, but if we expand that, final minus initial. So delta T is a shorthand for T final minus T initial. So if you actually wanted to do this algebraically, we found delta T. If you plug in 21 Celsius there, solve for T final. All right, that's another one of those. It's kind of like those conversions where it's more trouble than it's worth to actually show it algebraically because you already know what to do, like feet to inches. But sometimes it gets tricky. Are you supposed to add or subtract? So this is your way of showing your work, keeping track of your negative signs, etc. All right, good job today. See everybody on Wednesday. I'll have the rest of your test graded.
It's the, thinking about like, energy it takes to burn 3 grams of sugar